All right, and we're actually not only just getting back to notes, we're actually also going to a new unit. Unit 15, ecology. Unit 15, ecology. And we're starting off with 15.1. We're looking at population growth and carrying capacity. All right, so let's start by making a graph. Actually, before we make a graph, we have to make our data columns. There's a couple things I want to point out to you guys about graphing in general, and then graphing with this stuff. So good day to take notes and graphing, huh? So this is actually based on a real study. I think it was an island up in Michigan. And I'll be honest, I'm not sure if they reintroduced deer or if they just introduced deer for the first time. I'm not sure if deer had already lived there or that they went extinct or people hunted them. I'm not sure if deer had already been on this island, but for whatever reason, there's this island up in Michigan that didn't have any deer on it. And so they reintroduced them in 1971. That'll be our first year. They brought a population of 400 deer to this island. And then over the next decade, they charted this population's growth. Came back in 1972, and there were 480 deer on the island. 73, there were 639 deer on the island. 74, there were 891 deer on the island. 75, ooh, big number here. 1,114 deer on the island. And then it started going back down. 1976, 953. 77, 840. 1978, 720. 79. Okay, now it kind of stabilizes. And 80. Both the last 2 years have the same number of deer on it. Sorry about that. So the bottom part there, 79 and 80, both had the same number of deer on it. All right, so there's our data, and we're going to graph it. I'm going to make a really large graph because I got lots to add to it. In fact, I might even need the next page to continue all the stuff we need to add to it. So I'm going to use most of my page here for our graph. And then the first thing I want to comment, I see a lot of people do this, and it really just is not necessary at all. I think this goes back to when you're first learning to make graphs. Everybody always starts at 0, 0, but you don't have to. In fact, oftentimes you shouldn't. You do not have to start at the origin. So I'm going to start, well, my first data point, my first year is 1971. So put time in years on this axis, the year on this axis. And we're going to graph our population growth here. on the y-axis. Deer on the y-axis, year on the x-axis. And again, you don't have to start at the origin. A lot of people do, and sometimes it can really distort your graph. The point is we want to open this graph up and use as much of it as possible. If you're always starting at 0, 0, you're going to have a lot of wasted space on that graph. So just kind of first heads up there, you don't have to do that. Taking a look at our population of deer, let's say our minimum number is 400. Our maximum number is 1,114. I don't know, I'm thinking let's go 200, we'll say, up to, hopefully this works out. Hopefully I got the right number of lines in there, up to 1,200. That way I've got a number that's below my lowest number. I'll definitely be including 400 within that. In fact, you probably could even go all the way up to 300. That would include 400. And then 1,200 is a nice round number above my highest number. My highest number is 1,114. 1,200 definitely encompasses that, but it's also not like such a high number. I had to pick 2,000 to where this will only be halfway up my graph. Don't want to do that. So make sure, next point here, always make sure you guys are using at least 75% of your axes. B. Always make sure you guys are using at least 75% of your axes. Especially, I know it shouldn't be that hard when you're making your own graph because you can change the axes, but when I give you a graph, I expect you to use at least 75% of it up to this area. If your last data point is like right here, you're going to lose half a point. You've got a lot of wasted graph there. So let's see, we've got 10 years. I'm going to make sure I use my entire scale because I used it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. All right, next, I'm going to count how many blue lines I have between my 200 and my 1,200. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14, that's a nice whole number. If you wanted to be most precise, sure. So Yash would like to put years of the 20th century, so that's a better title, sure. I like that. All right, so we got 14 lines. We've got 1,000 data points, or 1,000 is our range from 200 to 1,200. Any suggestions? Here's mine. If our range is 1,000, I'm going to divide it by 14. Ooh, that's an ugly number, isn't it? Well, if we went up by 100, we have to change the top of our axes, so, which I suppose we could. Would you rather do that? Make it easy? That 71 is a pretty ugly number, so I'm kind of okay with that. So if we're going to go up by 100, do I have to draw every line? You can. You don't have to. So we'll call this 200, 300, 400. I'm going to say 500 right there. 600, 700, 800 right there. I'm going up by 300s then. So 900, 1,000, 1,100. And this one here would be our 1,200. So we're going to lose a couple lines if we do that. But again, since we're making our own graph, that works. That's okay. Guys, this is really important. You saw what we did there. This is probably the most missed mistake. All right, let me rephrase. Not putting a title is probably the most missed mistake, but this is probably the most missed mistake, and it drives me nuts. Bonkers. People miss this all the time. In biology, a lot of you guys are going to do it in your homework tonight, despite the fact that I'm harping about it. Chemistry, I see it all the time. You have to have even intervals. And I basically said every little blue line on my page is 100. Now, I didn't label them all, and that's fine, but every blue line was worth 100. That's an even interval. Some of you guys are going to do this in your homework tonight, despite the fact I'm harping about it. You just won't pay enough attention. Again, I get this in chemistry all the time. You guys don't have to duplicate this. Actually, I'm going to get a fresh sheet of paper for this. So just as an example, and you guys don't have to duplicate this, you don't have to put it in your own notes, but something just drives me nuts. Let's say 0, 1, 2, 3, 4, 5, 0, 50, 100, 200, 400, 800. All right, something along these lines, this type of growth right here. What I see a lot of people do is they just put these numbers right onto the grid. 50, 100, 200, 400, 800. And this drives me nuts. Look at these intervals right here. And right here, it's the same space on the graph, right? Roughly, it's not perfect. I'm not the best artist in the world, but it's about the same space on the graph. Why in the world is it worth 200 here and 400? How can the same space be worth different amounts? Down here, the exact same space is only worth 50. Ah, it's awful. You just didn't pay any attention. This is not even intervals. You hear me yelling at you about this. This is not even intervals. It's the same interval with a way different value between them. When you end up doing your graph, then it's really easy to grade because here's what I see. You just be shocked at how many people only ever make straight line graphs like that. In reality, this data should look more like this. So we've got an equal 150 interval between them all. And when you do it that way, do still start off there, and you do still start off there, but number 2, like right in there. Number 3, up here. Number 4. Number 5 is like way up there. You see the difference in these two graphs? You see how they make a completely different shape? That's a huge difference, and yet some people will always give me a straight line, and I go crazy because you just aren't paying attention to your equal intervals. These are completely different shaped graphs, completely different shaped. So watch out for that. Be careful. You get tested on that on your homework tonight. So I'm getting ready to nail you right away if you're not paying attention to even intervals. All right, let's plot our points then. 1971, we had 400 deer. 1972, we're up to 480 deer. It didn't go up that very much that first year. That's okay. 1973, 639 deer. Okay, so now we're starting to increase. Again, every blue line that I have is a 100. So I'm kind of guesstimating in between there. I think that's about 639. It's not quite halfway. It'd be 650. Bless you. 74, 891 deer. Whew, now we're jumping. So that's almost 900 deer here. 75, 1,100 deer. I'm gonna pause there with my data. Add a little note. Populations oftentimes grow, that word's exponentially. So that's when you kind of have this J-shaped curve. It starts off not so fast, and then it gets faster and faster and faster. So populations often grow exponentially because when you have more children make more babies. Just kind of how it works. When those children grow up and can reproduce themselves, if there's more children, they're going to have even more babies. And more babies means even more babies when they grow up. You know, so for humans, we're talking about like a 20-year life cycle here. So it's not as easy to grasp. But deer, who can reach sexual maturity within a couple of years, man, that population can really explode. I'm thinking about it this way. We mentioned this last week, we talked about sustaining populations. All I need to do to ensure that I'm doing my part is to have one offspring. That's it. That's impossible. I can't have an offspring by myself. It just won't work. No matter how hard I'll try, just won't work. So I need a spouse. So me and my spouse would need 2 offspring, one for each of us, right? And then all of a sudden, our population is sustained. We've done our part to sustain our population. What if I had 8 children now? And each of them have 8 children. How many grandchildren would I have? Yeah, I got 64 grandchildren now. You kind of see how there's like be a pyramid of growth. You know, me and my spouse just be 2 people, but 2 generations later, there'd be 64 of us. So populations can grow exponentially at first. But here comes the problem. Let's continue graphing. $953 and 76. So then we start coming back down. 840 and 77. James, notes. $78. We're all the way down to 720. And then we bounce back a little bit, our deer population bounced back a little bit to 760 on both of our last two data points. All right, we're going to add a line. We're measuring this through time, so we're going to add a line. We're just going to connect the dots here. And then something you guys should get in the habit of, circle your data points. Whoever's grading will appreciate, that's me for the time being, will appreciate being able to see your data points. It's just a good habit to have. Circle those data points of your growing population of deer and then shrinking population of deer. And the next thing we're going to take a look at, well, actually, before we get there, let's make sure we give this a title. Again, that's probably the most missed point that there is. And don't have to be anything too creative, but we're looking at what are we measuring? We're measuring the deer numbers in the 1970s. All right, sweet. Never forget that title. It's the easiest point for me to take off, and it should be the easiest point for you guys to get. I was grading the graphing you guys did last week, 2 weeks ago. You had like 3 graphs to make, and I just it's surprising how many guys forgot titles. So always don't forget that title. All right, here's the next thing we're gonna add. Right here, our population kind of stabilized. And 760 deer. That right there, that dotted line is what we call the carrying capacity. Which is the maximum number of individuals, in this case deer, but it could be any population. Think again in your homework tonight, you're taking a look at a human population. So the maximum number of individuals that an ecosystem can support. In that ecosystem, there are a lot of options here. Your ecosystem could be an island in Michigan, as it is. That's our whole ecosystem. Or it could be all of planet Earth, which again will be your part of your homework tonight. Next thing we're going to look at right here. Where we go above the carrying capacity. Is it possible for a population to go above the carrying capacity? Yes, absolutely. It's called the overshoot. The problem is you can't stay above the carrying capacity. It's not sustainable. The environment just won't support it, not for very long. something we call limiting factors are things that stop a population from growing indefinitely. They limit how big the population can grow. That's where the term comes from. And they kind of define an ecosystem's carrying capacity. They determine where that is. You're going to read about that in your homework tonight. I'll give you the easy one. Food. Food is a limiting factor. There's only so much food on the island for the deers to eat. What else? What's that? Excellent, yeah. Predators. Predators can limit a population. What else?
Water.
Water. Excellent. That's probably the biggest one. The amount of water. What's that? Excellent. Yep, another good one. You guys done this before? It's been a long morning already. Disease. 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 So I was right the first time? Oh. Disease. All right, I got a chat. Somebody chiming in from online. Yes, excellent. Person online says land or territory. Absolutely. How much space? What else? Shelter. It's another really big one. And yes, disease is a limiting factor. Diseases are much more prone to hitting high density areas, overpopulated areas. You guys remember about a year ago, all the news of COVID. Well, yeah, it was from Italy, but here in the United States, where were we getting hit the hardest about a year ago? California got kind of slow at first. New York City. Yeah, New York City got drilled first. Why? Well, it's like our greatest population center. So yeah, diseases actually tend to affect overcrowded areas first. Absolutely. It's easier for them to spread. Organisms are much closely packed. Also, weather, storms, hurricanes, tornadoes, all that kind of stuff can limit an area as well. There's probably more we're missing, but these are limiting factors. And again, they kind of control where that carrying capacity is at, how big a population can get. Can a population overshoot? Yeah, absolutely. You see it right there. But here's the problem. It's not definite. It can't stay up there forever. And you basically have two options. Here's a fact. You're coming back down to the carrying capacity. That is a fact. Here are your two options. You can either do it this way, like the deer did, or you can do it this way. Population crash. And this has happened. We have seen population crashes. The reason why this can happen is that you get so far above the carrying capacity, or you're above it for so long that you degrade the ecosystem. You can no longer get out of it what you expected to get out of it. And so where it might have at one time been able to support 760 deer, well, all the deer ate all the trees. There are no more trees at all, period. Now all of a sudden it could have supported 760, but there are so many deer that aren't any trees at all. The population crashes and it can get wiped out completely. It is definitely a possibility. So obviously this one is better. It's not good. You know, there's a reason why the deer population is going down right there. It's not good, but it's better than a population crash. That's bad. Bad news bears. Questions? That's not what I wanted to share.